So today we're going to continue solving polynomial equations, and I just want to remind you that in the last lesson we did a lot of solving of polynomial equations. So although I am going to go back over some of the things, if you want more details you should go back and look at the 5-4 video as well. So we've got a couple theorems that are coming into play here that'll be in questions in your quiz, and I am going to go through parts of them, and then they really probably won't make sense until we do the examples where we'll actually get to use them. So the first is Descartes' rule of signs. So it's not Descartes, it's Descartes. He was a mathematician, and his rule of signs is basically to show us the number of positive real roots that are possible, as well as the number of negative roots. And so we'll go through the details when we go through the example, but that's to find us, okay, how many roots do I have that might be positive? How many roots do I have that might be negative? The complex conjugate theorem tells us that if a plus bi is a solution of the polynomial, then a minus bi is a solution as well. The reason we call it the complex conjugate theorem is because these are complex conjugates. A plus bi is the conjugate of a minus bi, and vice versa. This works for radical conjugates too. So if you have a plus square root of b, then that means you're also going to have a minus the square root of b, and so on. So they always come in pairs. The reason why is you only get i's if you have a square root, and obviously with radicals you have a square root as well. So those always come in pairs. You're never going to have just one radical solution or just one imaginary solution. They have to come in pairs. So you either have none of them, or two of them, or four of them, six of them, so on and so forth. The upper and lower bound theorem helps us zero in on where our real roots stop, as far as there aren't any below this number or there aren't any above this number. And we use synthetic division to do that. The key when we're going through these is that C has to be bigger than 0 in order to have an upper bound, and the answer row of your synthetic division has to be all positive numbers. So both those things have to be true for C to be an upper bound. When we're looking at a lower bound, C has to be less than 0. You have to have alternating signs in the answer row in order to be a lower bound. So again, sometimes reading through the words or listening to me read through the words doesn't really make them make sense. So we're going to go through an example where we do a whole bunch of stuff with f of x here. So the first thing we're going to do is review from last time, list the possible rational roots. So the rational root theorem, which was in the last lesson, we have to list the factors of the constant, because that's our P over Q idea. So possible factors of 6, I can have 1 and 6, positive 1, positive 6, negative 1, negative 6. So these are both plus and minus, and all the factors always are. Or we could have 2 and 3. So positive 2, positive 3, negative 2, negative 3. And that's it. 6 is not evenly divisible by any other integers. Then on the bottom, Q, those are factors of the leading coefficient. My leading coefficient here is 2. So I have positive and negative 1, positive and negative 2, and that's it. Now, the possible rational roots are when I do each P value divided by each Q value. So I have to do 1 over 1, which gives me plus and minus 1. 6 over 1, 2 over 1, 3 over 1. So 2, 3, 6. And that takes care of using the 1 here. Now I have to do each of these P's with the plus and minus 2 in the bottom. So 1 over 2 doesn't reduce, that's 1/2. 6 over 2 reduces to 3, and I already have that in the list, so I don't need to list it again. 2 over 2 reduces to 1, also already in the list. 3 over 2 does not reduce, so that rounds out our list. These would be our possible rational roots. Find the number of positive real solutions. This is where Descartes comes into play. So what we have to do is we have to look at P of x, which is, in this case, f of x, and we count the number of sign changes. So we start out with a positive sign. It changes to negative, so that's one sign change. Here it doesn't change, it's staying the same. Here it changes back to positive, so that means there are two sign changes. And what Descartes tells us is that the number of positive real roots is either equal to its sign changes, so that means 2 real solutions, real positive solutions, or less than that number by 2, 4, 6, 8, so on and so forth. So if I take 2 and I go less than that by 2, I get 0. If I were to go less than that by 4, I'd have a negative number, which doesn't make sense. We're counting something, so it doesn't make sense to have a negative number of positive real solutions. So I either have 2 or 0 positive real solutions, which means I know for sure it can't be 1. So this is helpful to us. Then we're going to find the possible number of negative real solutions. So negative roots are equal to the sign changes in P of negative x. So I don't look at the original. I have to find f of negative x first, which means this notation means plug in negative x in place of x and simplify. So I'm going through the entire polynomial and I'm replacing x with negative x everywhere I see it. And then I'm going to simplify. So negative x times negative x times negative x, which is what this is telling me to do, is negative x cubed, times 2 is negative 2x cubed. Here, the squared, negative x times negative x is positive x squared. Positive x squared times negative 3 is negative 3x squared. Negative 11 times negative x is positive 11x, and then obviously this plus 6 doesn't change. So when I look at f of negative x, it starts negative, so this is not a sign change. This is a sign change, this is not. So that means that there is one sign change, which means that I would have 1. If I go less than 1 by 2, it's negative, so that doesn't make sense, which means it is exactly 1. 1 negative real solution. All right, D is 2, an upper bound for the zeros of f of x. So to do an upper bound, I said I'm dividing by x minus c. So in this case, we're dividing by x minus 2. So 2 is our value. We use synthetic division, it says. So I put 2 in there, and then my polynomial 2, negative 3, negative 11, positive 6. Put in my remainder separator and my horizontal line. Bring down the first coefficient. 2 times 2 is 4. Add the column to get 1. 2 times 1 is 2. Add the column to get negative 9. 2 times negative 9 is negative 18. Add the column to get negative 12. For upper bound, it says the answer row has to be all positive numbers. I have 2 negative numbers. So that means that this is a no. 2 is not an upper bound, which means that there is at least one real zero that's bigger than 2. All right, now is negative 3 a lower bound? So this is like dividing by x plus 3, remember, because we changed the signs there. So negative 3 goes in my outside and then copy my coefficients again. Remainder separator, horizontal line, and bring down. -3 times 2 is -6. Add the column to get -9. -3 times -9 is +27, which gives me +16 when I add the column. -3 times +16 gives me -48. Add the column to get -42. So lower bound, right here it says, we know C is less than 0. Yes, -3 is less than 0. We need the answer row to have alternating signs. That means it goes from negative to positive to negative to positive, or vice versa. So positive, negative, positive, negative. So this is a yes. Yes, -3 is a lower bound. So that means that there are no real solutions that are below -3 on the number line. F, this one's a simple one. How many solutions does f of x have in the complex plane? This goes back to the fundamental theorem of algebra. You look at the degree. Degree 3, 3 solutions, or 3 roots, or 3 zeros. All right, so now we're actually going to find them, and we're going to do this the same way that we did in the last lesson. So first, I'm going to graph this equation. So 2x cubed minus 3x squared minus 11x plus 6, either on Desmos or your graphing calculator. So here it was, the equation typed in there in Desmos, and here's what I can see. So I can see 3 real zeros. It doesn't matter which of these I pick. I'm just going to start with -2. And so we put that in for our synthetic division to -3, -11, and 6. And go through the process. This gives me -4, column gives me -7. +14, 3, -6, 0. Remember, you have to get 0 if you're confirming. Now, what's left, because my original is cubic, is a quadratic, so that represents 2x squared minus 7x plus 3 equals 0. And then I'm going to factor it. So 2x, x. Because this is a plus and this is a minus, I know they're both minus. So 3 here, 1 here. And if I check my FOIL, that gives me -6x minus 1x, which is -7x. So I know it's right. Then I set each of those factors equal to 0. And I solve them. So I get x equals 3. Add the 1 here to get 2x equals 1. Then divide by 2. X equals 1/2. So I have x equals 1/2. X equals 3. And then right up here, I confirmed the x equals -2. Again, 3 solutions, so I found them all. H, write f of x as a product of its linear factors. So remember that if 3 is a solution, that means that x minus 3 is a factor. So this is the factor theorem from last time. If x equals -2 is a solution, that means x plus 2 is a factor. Remember that the 1/2, we have to do 2 steps. Multiply by the 2 first, then subtract the 1. So it gives us this 2x minus 1 as our factor. And so this would be the answer there. We don't have to do any extra work. We already did it in part G. All right, last thing we want to talk about is if the given expression is a root of the polynomial, what else must be a root? So this is the complex conjugate theorem. So here I have 19 plus 2i. I know if that's a root, that its complex conjugate must be also. So 19 minus 2i would be the answer. This one, it's radical conjugates, but it's the same idea. If 6 minus radical 11 is a solution, then 6 plus radical 11 must also be. So we use root, solution, 0. Remember that all of those mean the exact same thing. All right. Like I said, if you need more review on the actual finding of the roots or the linear factors, you can look back at 5.4. This one focuses a lot on these new theorems, so make sure you reach out if you need help.